In this video, I want to talk about proportional reasoning. Proportional reasoning is a key tool in your mathematical toolbox. It's something that physicists, scientists, and engineers use all the time in working with proportional relationships between quantities. And so if we say that A and B are proportional, what does that mean? One way we often write that is we say A is proportional to B in this way. We use this symbol here that looks something like a Greek alpha, but that's a common symbol that says A is proportional to B. What that means is that you can write a relationship where A is equal to C times B, where C is a constant. And so, well, that's a simple equation. Why do we need a whole video to describe reasoning this sort of simple expression? Well, if you get very proficient with proportional reasoning, you can solve problems. I say many types of problems without knowing what C is. Without knowing C. But even more important, you can solve many problems much faster. And that's a very important part. We're often about solving problems as quickly as we can, and being good at proportional reasoning lets you solve a lot of problems much, much faster than if you go through a straightforward approach of substitution or standard ways of solving algebraic expressions. So let's just look at a couple things that this sort of relationship means. It means, first of all, that, say, if B doubles, that implies that A doubles. And the same thing, if B triples, then A triples. If B goes up by a factor of 10, then A goes up by a factor of 10. Let's say, for example, that C is equal to 5. If we were to look at a table of A and B, if we say B is equal to 1, 2, 3, and 4, then A is equal to 5, 10, 15, and 20. And so, again, in fact, if, say, B is cut in half from 2 to 1, then A is cut in half from 10 to 5. B is quadrupled from 1 to 4, then A is quadrupled 5 to 20. And so, instead of using substitutions, we can just see how they both vary in proportion to each other. So that's one quick way to look at this. Another way is to consider ratios. Given this relationship, the ratio A over B, which is equal to C, is constant. And for any set of values, A and B. And so, for example, if you're given something that for one value of A, which is 6, results in a second value of B, which is 10. So, and then maybe we want to know what is B2 if A2 is equal to 9. Now, instead of trying to use this to solve for C and set up two equations and substitute, we can use this proportional reasoning in this ratio to find it directly. We know that A1 over B1 is equal to A2 over B2. And this gives us that B2 is equal to A2 over A1 times B1, or this is A2 is 9, 10 over 6. And if this is 3 and 2, 1 and 5, thus this is equal to 15. So here's an example where we were able to solve for the answer without ever even evaluating what that constant of proportionality is. So another way to look at this is that A1 over A2 is equal to B1 over B2. And so these ratios also allow you to solve problems without ever finding the constant of proportionality. Okay, so that's simple enough, but let's expand it a little bit. We often refer to not just systems that are proportional to each other, but we encounter systems where A is proportional to some power of B. And so what does this mean? Well, this means that A is proportional to B to some power n. And now let's just consider situations where n is greater than 0. So this means that A can be written as some equation with some constant here times b to the n. C, again, is constant. And so we have a similar idea that we had before, but now we have this extra power of n. And so if we do some proportional reasoning on this type of relationship, we might often say if we increase B by a factor of some factor, we'll call it a factor f, then A increases by the factor f to the n. So if B doubles, I'll write that as times 2. So if B increases by twice the amount, that means that A increases by a factor of 2 to the n, depending on what that power of n is. If B triples, we increase B by a factor of 3, then A increases, I'll use a little arrow meaning increases so I don't have to keep writing it, by a factor of 3 to the n. And so if we look at the ratios, we see that A over B to the n is equal to a constant. And that also means for any two sets of A's and B's, A1 over A2 is equal to B1 over B2 to the n. And we can see that really easily if you don't, if you just can't see it immediately. If I have some value A1 is equal to C B1 to the n, and A2 is equal to C B2 to the n, I can just divide these two equations. The C's cancel, and I get A1 over A2 is equal to B1 over B2 to the n power. So let's just look at a quick example where this might work. So let's consider a sphere, physicist's favorite object, the sphere. It has a radius, r, and a constant density. Constant density. All right. For such an object, the mass of that object is proportional to the volume. And so we might look at that relationship. However, volume is proportional to the radius of the sphere cubed. And so, therefore, the mass is proportional to the radius cubed. And so we might write that m for mass equal to some constant r to the cubed. And you might already know what that constant is, but maybe we don't need to use it or know what it is if we can use proportional reasoning. The mass is proportional to the radius cubed. So in this case, if the radius doubles, that means the mass increases by times 8, 2 cubed. If the radius triples, that means the mass goes up by 27, or 3 cubed. In fact, if the radius, for example, goes up by a factor of 10, then the mass goes up by a factor of 1,000, or 10 cubed. So let's just say if we had a radius is equal to 0.1 meters and a mass of 3 kilograms, if we increase the radius then to 1 meter, that's by a factor of 10, then our mass, so here, if this is R1, R1, then if R2 is equal to 1 meter, then our mass 2 is 3,000 kilograms. Our mass increased by a factor of 10. Our radius increased by a factor of 10, rather. Our mass increased by a factor of 1,000. So that's proportional reasoning, where we have a one quantity, say A, is proportional to the power of another. I want to look at one more different type of proportional reasoning. It's not really different, but we often use different words. I'll show you what I mean. We sometimes talk about inversely proportional. Inversely proportional. And so we might say A is inversely proportional to B. And so what we usually mean by that then is A is equal to some constant over B, or A is proportional to 1 over B. We can also say that A is inversely proportional to some power of B, and so A is equal to some constant times B to some power n, where n now is here greater than 0. Or we might say A is proportional to 1 over B to the n. Now, you might say that, look, we don't really need to speak this way. This is really just a separate class of expressions that we had before. A is equal to C, B to the n, where n is less than 0. That is essentially mathematically equivalent to this sort of expression. And that's absolutely correct. It's just that in the language that scientists and engineers use, we often refer to expressions of this type as inversely proportional instead of sort of a generic proportional to some power to the negative n. So let's just see the differences that this creates. So in this case, if I increase, and I'm going to use little arrows to mean increase, if I increase B by a factor of 2, that means I decrease A, or A decreases by a factor of 2 to the n. Or if I increase B by this time a factor of 10, that decreases A by a factor of 10 to the n power. So if I want to look at relationships, I can say that A, B to the n is equal to some constant. Again, if I want to look at it in terms of ratios, I would say that A1 over B1, I'm sorry, A1 over A, let's do A1 over A2. A1 over A2 is equal to B2 over B1 to the n. And you can see it's the same as before, except the b's are inverted. Where here this was B1 over B2 to the n. I now have B2 over B1 to the n. And so I can again use these proportional reasoning to solve problems without ever solving for what this constant happens to be. Let's just look at, for an example, let's use Newton's law of universal gravity. Newton's law of universal gravity says that the gravitational force, the gravity force on a mass m by a mass capital M is proportional to each mass and you may not have seen this before. We've done videos here where we've looked at gravity near the surface of the Earth, but this is now Newton's universal law of gravity, and you may not have seen this yet, but that's not, it's not important. I'm going to describe it here. So the gravity force, the magnitude of the gravity force on a mass m by a mass capital M is proportional to each mass, and inversely proportional, I don't know how to spell inversely, proportional, whether this E is supposed to be there or not, proportional to the distance squared. So if I were to represent that mathematically, I'll go over here. That would say that this force is proportional to each mass, m times m, and inversely proportional to the distance between them squared. I'll call r now the distance between them. So what happens to the force between two objects if the distance between them doubles? If I want to compare the ratio of two gravitational forces, F1 and F2, that ratio is going to be the ratio of the two masses, m1 times capital M1 over the small m2, capital M2, times R2 over R1 squared. And so I'm using our laws for the ratios of proportional as well as inversely proportional. And so now if I have the same system, so M1, the masses are the same, but I've simply increased the distance between them by a factor of 2, that means the ratio R2 over R1 is equal to 2. So that this entire system just becomes 2 squared, or 4. And there, if I solve for F2, then the second force is equal to 1/4 the original. So by doubling the distance between two objects, my gravitational force goes down by a factor of 4. And so this is using proportional reasoning for systems that are inversely proportional to some power.